So our next lecture is gravitational fields, and this is still part of 6.1 in your textbook. It's just a bit further into that section. Now, the universal law of gravitation tells us that at any point in space surrounding a massive object, such as the Earth, we can calculate the gravitational force on a second object sitting at that point in space. So what we see from this image here is there are different g vectors. So g, that little g, is the gravitational field effect of Earth, and the closer we are to the planet, the longer that arrow appears, and that implies that the greater the magnitude of g is. So the closer we are to the planet, we have a greater magnitude of the gravitational field strength. Now, for a massive object, or any mass, it has a gravitational attractive force that is pulling everything towards it. So the idea of a mass having this gravitational field effect where all of these gravitational forces are pulling towards it is valid in this case. Now, when we have a situation like this, where we have a series of vectors and they behave in a predictable way, we call it a field. And when the force that is being demonstrated is a gravitational force, then we call it a gravitational field. So this slide here, it says basically that inside this gravitational field of the Earth, or any object, any point around the Earth is affected by the vector that exists at that point. And that vector direction is always pointing towards the center of the object. The magnitude is greater if we're closer to the object and less if we are farther away from the object. So I'd like to copy this down. A gravitational field is a field of force that exists in a region of space around an object. It is a vector quantity. We use lowercase g to represent it, and we often give it a subscript for the planet or the body. So it might be g of Eris, which is what we saw in the previous lecture, one of the sample questions. The gravitational field exerts an attractive force on objects with a mass. So a gravitational field will always exert an attractive force. There is no repulsive gravitational force, which makes gravity very different from the other types of fundamental forces. Gravity is always attractive. It can be represented by a series of lines directed radially inward toward the mass, and that's the gravitational field. These lines, or arrows, should be greater the closer they are to the center, and smaller the further they are from the center. This note is important. I'd like you to copy this as well. It says the fundamental concept is that a field is a property of space. An object influences the space around it, setting up either a gravitational, electric, or magnetic field. The object producing the field is called the source. This field in turn exerts a force on other objects located within it. Now, the field itself, we can give it a value, and then we can define that as the gravitational field strength at that point. And to do that, there is a formula. It's pretty familiar. We'll get into that soon. But that gravitational field strength, we measure it in newtons per kilogram. So how much force per unit of mass does an object experience at that point in space around the source, the gravity source? You will notice that newtons per kilogram is equivalent to meters per second squared. And you could use the two interchangeably, although convention is that when we're working in physics and we talk about gravitational field strength, you would use newtons per kilogram as your unit and not meters per second squared. And again, on this slide, it does say that 9.8 newtons per kilogram is the gravitational field strength of Earth. It should say at the surface. It doesn't say that, but that's the gravitational field strength at the surface of Earth. Another interesting thing to note is that the gravitational effect is the same at kind of any sort of circular shell around the Earth or any object. So at the surface, you can consider that as a circle. This is if the Earth was completely spherical, but for our purposes and our understanding, let's just consider it is. At that circular sphere around the Earth, it's 9.8 newtons per kilogram. At a point that is a bit farther away from the Earth, it might be smaller. It could be 5 newtons per kilogram at any location that is that radial distance away from the Earth. So it's a shell around the Earth that would experience that newtons per kilogram. So the gravitational field strength can be thought of as different shells of strength depending on how far you are away from the source, the gravitational source object that we're comparing it to. So here it says for spherical objects, the strength of the gravitational field at a distance from its surface is the same whether the mass actually fills its volume or it sits on a point in the center. So to calculate the gravitational field strength as a function of a central spherical mass, we can use Newton's second law with the Universal Law of Gravitation. We did this in the previous lecture when we figured out the gravitational field strength of Eris. Fg equals Fg. We can calculate Fg using ma, where m is the mass of the object and a is our lowercase g. And Fg, the force of gravity compared between two objects, is also our big G times the product of the masses divided by the square of the distance. And if we have these two equations set as equal, we would find that m object can be divided out on both sides. So we're left with our G being equal to our big G times the mass of our planet times r squared. So the gravitational field strength is calculated irrespective of the mass of the object. No matter what the mass of the object is, it'll experience the same lowercase g. So this equation holds for any object in the gravitational field, right? It's the lowercase g is only dependent on the mass of the large body that we're looking at. So I'd like you to copy this down. Gravitational field strength is the force of attraction per unit of mass. It is 9.8 newtons per kilogram if we're looking at the surface of the Earth. It is calculated using this equation here. G equals big G times the mass of our planet over r squared. We write MP because it could be any large object. Usually it's planets, or it could be a star, it could be any other celestial object. So an object's acceleration due to gravity does not depend on its own mass is another point. I'd like you to copy that down as well. So we'll go through a couple quick problems here, and then I'll leave a few for you to look at as well. It says here, calculate the magnitude of the gravitational field strength on the surface of Saturn, assuming that it is perfectly spherical with a radius of 6.03 times 10 to the 7 meters. And the mass of Saturn is 5.69 times 10 to the 26. So we're going to pick up our G, which is 6.67 times 10 to the power of negative 11. To the power of negative 11. And I'm going to save that in my memory because I'm going to use it again later. So our lowercase g is calculated using that big G times the mass of our planet, which in this case is Saturn, so it's 5.69 times 10 to the power of 26, divided by the radius of the planet squared. So 6.03 squared divided by 10 to the power of 14, because 7 squared would be 14. It gets us to 10.4. Looking back at the question, we have 6.03, we have 5.69, so 3 significant digits, 3 significant digits. We used 6.67 for G, so that was 3 significant digits, so we report our answer with 10.4 newtons per kilogram. Another question to look at, it says on the surface of Titan, which is a moon of Saturn, it says the gravitational field strength is 1.3 newtons per kilogram. We have Titan's mass, we're asked to find out what Titan's radius is. So if we rearrange that equation, we start with G equals gm over r squared. We have to rearrange that to find out what r is. So that would be r is equal to the square root of g times m divided by g. So we can take our g, the big G, divided by our little g, times our m, and we'll have to find the square root of this. We get 2,582,000, which is 2.58 times 10 to the 6. But if I look back at the question, I have 2 significant digits, so I have to round this to 2.6 times 10 to the power of 6. Now these next 2 questions I want you to practice on your own. The answers are there for you, so you can just use these as additional kind of homework. It says here, suppose that an object expanded until its radius doubled while its mass stayed the same. Determine the effect on its gravitational field strength. So I won't tell you how to do this, but if you have any trouble, just post it in the discussion board. And the next question 4, it says, suppose the mass of a planet doubled, but its radius stayed the same. Determine the effect on its gravitational field strength. And same thing here, I'd like you to try this out on the lecture or in your homework, in addition to the other problems that are listed. If you have any trouble, again, you can mention on the discussion board that you need help, or you can send me an email if you want to remain anonymous.